Now we go to the official website of IBM Quantum Computing and try IBM Q Experience. Try it out now and log into your account. Now we go to the circuit composer and new circuit, and we'll change the name to let's say Quantum Teleportation. Okay, and we save the result, save the title, and then we start building our quantum circuit. So the first thing to do is to create bell state between Q1 and Q2, and we can do that by applying Harman gate and a CNOT gate on it. And then we need to create entanglement between Q0 and Q2, and then use H state to shuffle Q0 qubit. And then we need to implement the classical control gate, and we can change the classical control gate to a quantum control gate. So we need controlled X gate and control Z gate. And control X gate is basically the control NOT gate that we apply from Q1 to Q2, and we need another control Z gate from Q0 to Q2, and for that we need to double click on the CZ gate, and you see that C is the control qubit and T is the target qubit. So now the qubit 0 is the control qubit and qubit 1 is the target qubit. We want to change the target qubit to qubit 2. We just need to drag and pull. And you already see that this is CZ, this is the control Z gate, and you see that it is already updated. And the reason why control Z gate is symmetric, it's because it is indeed symmetric with respect to a target and a control gate. Yeah, so you can change the target and control gate freely. So that's why the icon is itself is also symmetric. Okay, so now this is basically a circuit, and we need to measure. So we need to measure first one, second one, third one. Yeah, and before we run the experiment, we can already get some information from the visualizations here. That, for example, we go to the measuring probabilities, and the rightmost qubit is qubit 0. Yeah, so you will find that what we are interested in is actually the measurement on qubit 2, and that is basically the middle digit. And you see that the middle digit is always 0, so it's 100% 0. And the reason is that we teleport the state on the Q0 qubit, which is 0, to the Q2 qubit that is 0. So that's why it's 100% 0. If we measure, if we change this to 1, change the initial state that we want to teleport to 1 by applying X gate on 0, and it results in 1, and you will see that the middle digit goes to 1, like 100% 1. Then, for example, we can delete this X gate and change it to RY gate, and RY gate means that you rotate this state along Y-axis, and in our case we can double click and change it to 2 pi over 3. Yeah, that is 120 degrees. And in this case, you will find out that this is basically 25% and 75% to be 1 and 25% to be 0. And the easiest circuit would be that we delete this RY operator, and we just want to teleport this 0 state to here, and then we will see 100% of 0 state here. And then we save the changes and run on this Vigo machine. Go to the results page and wait. Now it's finished. And now we go to the fresh result. Yeah, and in principle you need to add those up to give the probability of 0, and those up to give the probability of 1. And we expect to have 100% 0, so those are the errors. And if you add those up, that is around 8%. So we have 8% error in this quantum teleportation, simple quantum teleportation circuit. Okay, and then we can do something more complicated. We can basically add RY rotation here and change this to 2 pi over 3. That's around 120 degrees. And we will just run this code and save the changes and run. And we are not interested in the simulator, but of course, if you are not sure, you can also first run it on the simulator. But in this case, we can run it on this Vigo quantum computer and 4000 shots. And we run, and we can check the result in the results tab here, and it's in queue. We just wait a little bit. Okay, so now it's finished. We refresh the completed list, and then the first one. And you see that this is the result, and you need to add those up to give the possibility of 0, and add those up to give possibility of 1. Yeah. Okay, I'm not going to do that, but I'm going to just change the circuit. We can remove those two measurements here according to the principle of inferred measurement in quantum circuit, and then we run this again. Okay, this has already been given to the quantum computer, and then we go to results tab, and we need to wait a little bit. Now it's finished. We refresh the completed list, and then go to the fresh result here, and then we will see that it's 40% 0 and 59% 1. So it is there's still some deviation from 25% to 75%, but this is because of the error of the quantum computer. Okay, so with that, I would like to go back and show you some possibilities of further practice. I have shown you how to construct a quantum teleportation circuit on IBM Quantum Computer, and actually you can do more practices to be more familiar with the fundamentals of quantum mechanics. One thing is that you can try to remove the measurements on the auxiliary qubits to see whether it changes the result, and verify the principle of the quantum circuit. And then you can construct other equivalent quantum teleportation circuits and test it. And then the third question is that what happens if we move the Bell state far away? You can increase the time elapse between the Bell state and the teleportation circuit, which mimics the time for the entangled photon to travel from Alice to Bob. Yeah, so it will suffer from decoherence, and the information will be lost after the decoherence time. That is the shortcoming of this quantum teleportation and quantum computation. Okay, thank you for watching. I hope you learned something. If you like my video, I appreciate your like or subscribe to my channel, and I hope to see you next time.